Hello everyone, welcome to our introduction on spectral clustering. My name is Kevin.
My name is Byron.
Today we're talking about spectral clustering of connected graphs. We will first go over the definition of clustering in a graph theory context. We will then use mathematical tools to define what are good clusters. For the scope of this presentation, we only consider two clusters. That means we are partitioning our graph into two parts. Then we will propose a time-efficient algorithm that will help us to find the best two clusters in any connected graph.
First, we will talk about what a good cluster is. Particularly, we want to define what clusters are in a very big, messy graph. The idea of clusters usually appear as a data science concept. It refers to a group of data points that gather around some value on the plot. If we look at the graph on the right side, we can see that data points have different colors on the map, which corresponds to different clusters they're in. So, if we take a closer look at these two graphs, we can see that data points within the clusters are usually very close to each other, but two data points from different clusters are far away. Now, we want to borrow the idea of cluster from data science to graph theory. To do so, we first make a definition of what clusters are in the graph. Essentially, a set of clusters in the graph is a partition of the vertex set. If the clusters we find behave in the similar properties as the clusters in data science, we say that they are good clusters. We will mathematically define these behaviors later. Our essential question is how to find a good cluster when we are given an extremely large and messy graph. The graph on the left is just a randomly generated graph with 50 vertices, and the graph on the right is a social connecting network outside the student center. We encourage you to try to find good clusters on these two graphs yourself. But you might want to ask, what even is a good cluster? Let's first look at some examples of good ones and bad ones. In this example, the blue clusters are better than the red clusters because to separate the red clusters, we need to remove one more edge than blue clusters, which means red clusters are more related to each other. In this example, although in both graphs we only need to delete one edge to separate clusters, there are 6 vertices in one cluster and only one vertex in the other cluster. The sides of the two clusters are very unbalanced. We do not want that to happen to our good cluster. So the two key observations we made from these two examples are, to get a good two cluster, we only need to delete as few edges as possible. Also, two clusters must be balanced in size. That means they need to have a similar number of vertices and edges from the induced graph of the clusters.
Next, we introduce some mathematical tools to define good clusters that satisfy the observations we made from the two examples. First, we define the volume of a cluster. A volume of a group of vertices is equal to the sum of degrees of these vertices. We can see that volume captures the idea of the sides of a subgraph. For example, a large subgraph would have more vertices in it, which contributes to a larger volume. Also, a denser subgraph would have more edges connecting its vertices, which also leads to a larger volume. And here are some examples of calculating volumes. If we look at the tables on the left, C1 denotes the vertices in a cluster, and the second column represents the volume of our choice of C1. We see that as we add more vertices into C1, the volume increases, which is consistent with the idea of the sides. Next, we define the conductance of a subgraph. To do so, we first need the idea of edge flux. The edge flux of two clusters, C1 and C2, is defined by the number of edges between C1 and C2. It quantifies the numbers of edges we need to delete to get these two clusters. Then the conductance of C1 is simply defined as edge flux of C1 and C2 divided by the minimum volume of these two clusters. To find good clusters, we want to minimize edge flux, which corresponds to deleting a small number of edges, and we want to maximize the minimum value of the two volumes, which corresponds to the balance in size properties we want for good clusters. Therefore, all we need to do is to minimize conductance. Here are some examples of the conductance we computed for different choice of clusters. We can see if we choose A, B, C to be our cluster, we get the minimum conductance. Also, if we look at the graph itself, A, B, C do give us a good clusters as opposed to the other choices.
Now for the exciting part, how to find a cluster that gives minimum conductance. A possible way to find minimum conductance is to consider all possible subsets of V and calculate the conductance of each subset S to see which one gives us the minimum. But for a huge graph, we cannot really go through all the possible subsets because it would take us forever to do it. But there's a better way. We introduce our friend the Laplacian matrix of a graph. In fact, the Laplacian matrix gives us information about edge flux of a cluster. For any given cluster C1, we can express it with the vector x, where the entries corresponding to vertices in C1 are 1 and otherwise 0. If we take the quadratic form of this vector with the Laplacian matrix, we get the edge flux of C1. What a miracle! For now, we can take a leap of faith and just believe that this fact is true. Therefore, we can narrow down the number of possible clusters we need to check by first finding a vector x whose corresponding cluster minimizes edge flux. This converts our problem to linear algebra, because right now we are just dealing with the minimum value of the quadratic form x transpose Laplacian x. We notice that since edge flux is always non-negative, the Laplacian matrix must be positive semi-definite. So the minimum non-zero value of the quadratic form is achieved by the eigenvector of the smallest non-zero eigenvalue. Note that we want to find a non-zero eigenvalue, so we need to exclude 0, which is in fact a valid eigenvalue for the Laplacian matrix. Here's the complete algorithm for spectral clustering. We first find a good approximation of the eigenvector x prime of the smallest non-zero eigenvalue of normalized Laplacian, which we will define later. We then use the power iteration method to do it. Next, we sort the vertices of V according to entries of x prime. Then, we iterate over the clusters Si each time adding Vi to the cluster. For each iteration, we calculate the conductance of Si. Finally, we return Si with minimum conductance.
Next, we demonstrate how our algorithms would work on the right side of the graph. For step 1, we need to first find the Laplacian matrix, which is matrix L. Then we find the normalized Laplacian matrix N using the diagonal values of the original Laplacian matrix. The idea is to normalize each row and column using the same weights so that the diagonal entries of the normalized Laplacian are all 1. Then we find the eigenvalue of the smallest non-zero eigenvalue of n, which is the column vector in the middle of the screen. This will be the vector x prime. For step 2, we sort the vertices in non-descending order of their entry values in x prime. We can see that the second and third column in the table corresponds to the sorted vertices and their corresponding entry values in x prime. Next, for step 3, we iterate through all the vertices in the sorted order. Column 4 shows the vertices in the cluster during each iteration. After iterating through all the vertices, we find that the conductance is smallest at iteration 4. This will be the output of our algorithm.
We also provide a video demonstration on how this algorithm will work in action. The input of the algorithm is any sparsely connected graph with 20 vertices. We can see in the video that during each iteration, the vertices that turn green correspond to the clusters Si, and the vertices that turn red correspond to the clusters that yields the minimum conductance among all previous iterations. Finally, our algorithm outputs the conductance in the clusters we found. Here are some example outputs. We can see that most of them make sense to what we would intuitively consider the clusters are on the graph. Graph clustering has a lot of applications in real life. With a faster algorithm in action, we'll be able to deal with larger graphs that contain more information even more efficiently. Also, spectral clustering bridges combinatorial algorithms with continuous optimization. This is a very important step in computational math because it signifies that maybe there really exists a universal algorithm that can solve any problem we have. Thank you for listening.